Alrighty, and so what we're going to do is the last bit of videos talking about some tension forces of blocks hanging by a string. And then we're going to do one last example of some special derivations of a formula of a block on a ramp and the coefficient of friction. So what we're going to do first is we're going to draw a system in which my mass is hung by two strings. We're going to call these strings the same angle of respect to the horizontal. And let's see what we got overall. First thing you do, anytime you do a force question in AP Physics, the first thing Mr. Williams wants you to do, draw a free body diagram. So we're going to have weight, tension, and tension. With this, I can now say I'm going to take my object, scale it up a little bit, and move it off to the side. Anytime you do a free body diagram, you don't touch it. Put in a little box of do not touch. And then we redraw our system so I can look at our components. And let's do that. So, using the same color, hopefully the same color, let's draw my system really quickly. Try that again. Alrighty. I got tensions off at some angles. Let's use brown again so we stay consistent. So we got weight going downwards, tension going up, and tension going up. What I'm going to do now is I'm going to draw my arrows looking at my components. So overall, what I've got going on is I've got forces in the x direction and I've got forces in the y direction. So force applied, I'm going to say force of tension. So we'll say tension in the x direction, tension in the x direction, tension in the y, tension in the y. Now that I've got my components broken up, let's go ahead and write out our equilibrium statements. So what I'm going to do is take this little piece right over here and let's write our equilibrium statements down below. Now, what I've got overall is we're going to say that the summation of my forces in both the x and the y direction are going to equal 0 because this object's not moving. So what I can say overall is that in the x direction, tension x equals tension x. Now if these are at different angles, what I would be able to say is then get to some more trig calculations, but since these are going to be set at the same angle, I can't really say much there. However, in the y direction, we can say weight is equal to tension y plus tension y. Using a little bit of our trig, we can say that the sine of our angle is what is going to equal tension y. So tension y equals t sine theta. So mg equals t sine theta plus t sine of theta. Overall, this is how you're going to do these problems and looking at tension forces of things being held by ropes, things being held by cables. There is a couple of interesting things that I want to note. If I have an object that is being held, let's say at uneven angles, where one angle is more than the other. So let's do a steep angle, and let's do a short angle. All right. What I'm going to say is that we'll call this tension 1, and we'll call this tension 2. Since this object is being held more overhead of the second cable, tension 2 is always going to be less than tension 1. So tension 1 is going to be greater than tension 2. And that's because this cable overall has to span a huge angle in the x direction. And so what you get is that as an object gets further and further, where this angle theta gets smaller, your tension gets bigger and bigger. So if we did a graph of, let's say, the angle theta to the horizontal and tension overall, you would get a very interesting function as you decrease your angle, it'd be an exponential function, and then this eventually would approach infinity. Problem you're under there is at one point this cable is going to snap. So what if I could say, for example, if I had something held perfectly in the horizontal direction. If I held something perfectly in the horizontal direction. Let's try this out. If I took my object and tried to hold it perfectly horizontal by two strings, the tension in both strings would have to read infinite. And that's because the sine of theta, where theta equals 1 or 0, is undefined. So you can't hold anything out perfectly horizontally because the tension would have to be infinity, because sine, another way to see that out is that sine of 0 is undefined. What if I were to say, for example, instead of this being held perfectly horizontal, what if we took it the other direction? What if I took my object and I held my strings straight up? Well, then what you then find out is that the weight of your object is going to equal to tension, and so that you essentially, all you do is you take the trig out of the equation, because these two things are no longer fighting each other. So mg would equal 2t, tension equal mg all over 2. All right. Now what we're going to do is we looked at tension forces. We looked at tension forces if I were to do them at equal angles, but the first angles, equal angles, and looking at some of those calculations you can make from that. Then we looked at if I took my object and then made that angle theta smaller, tension would approach infinity. If the angles are uneven, whichever angle is more towards the horizontal, that's where tension is going to be larger in. And then we looked at if I tried to hold something perfectly horizontal, tension would be undefined, and very often your object would just snap. Last one is if I held two cables holding an object, that weight would just be 2t because there's no horizontal component to your forces. And then the last thing I want to do, kind of off the cuff, what if I have an object that is not moving on a ramp? So let's do this. Let's take an object at some angle, and then let's put that object on a ramp. What would happen to my object? What is the coefficient of static friction only knowing the angle of which your block is at? Well, first thing I'm going to do is I'm going to draw my free body diagram. So I've got weight downwards. I'm going to have force normal upwards. And I'm going to have frictional force going back. And that's going to be frictional force of static friction. Now what I'm going to do is break out my components. So what I'm going to do is take this thing and make him go really small and move him off to the side. Redraw my forces. This time I'm going to draw them a little bit bigger. Force normal and weight. Break these into its components. Let's try that out. We're going to have weight perpendicular and weight parallel. What I'm then going to say is for my equilibrium statements, if this system is not moving, That means the summation of all my forces are going to equal 0. That means force normal is equal to weight perpendicular. And that also means weight parallel is equal to statical frictional force. Force normal is going to be, we're going to leave that alone. And weight perpendicular is going to be cosine of theta. So weight cosine theta. Weight parallel is going to be weight sine theta. And statical frictional force, I'm going to rewrite as mu sub s, force normal. You might see where I'm starting to go at since I got force normal over here, force normal over here. Take a real quick step back though where I got these two components of weight parallel and weight perpendicular. If I redraw my triangle, I've got weight perpendicular, weight parallel. What I'm going to then say is that sine of theta is going to equal weight parallel. Oop, getting a little crazy there. Over weight. And cosine of theta equals weight perpendicular over weight. These two equations you reuse and you bring over here. So that's where weight cosine theta and weight sine theta came from. Now what I'm going to do is take force normal and bring it on over here. So I'm going to bring these two formulas together. So weight, which is going to be mg sine theta equals mu sub s mg cosine of theta. I'm going to divide both sides by mg cosine theta. And we're noticing, hopefully, some interesting things going on. Mass and gravity cancel out, so I get that the coefficient of static friction of an object that is not moving is sine theta divided by cosine theta, which is also denoted as tangent theta. Interesting physics.